Okay, hi, good evening. So this is going to be the solutions and mixtures part 2. We're going to look at dissociation equations and molarity of ions in solution and particulate level diagrams. And I've come to realize, I'm sorry for you, that there will be a number 3, okay? There will be a number 3 video, I know. That's all I can do to keep them short, okay? So I'm going to share my screen. Come here. I'll be honest as well. Again, I've made this video a couple times and I keep making mistakes, so they just I don't like them. Which means they must be really bad, right? Okay, so we're going to get it right this time. Let's see. Let's talk about dissociation equations. And they show how different types of compounds dissociate when dissolved in water. All right, and you know that ionic compounds dissociate to form ions in solution. Right, and when we say dissociate, we mean dissolve. Okay, so let's put our typical ionic compound as a solid. Let's put that guy in some water and let's observe that what we end up with are the respective ions, right? Another example, Na2S. Let's put the solid into water. When it dissolves, we get now 2 sodiums for every sulfide ion. All right, those are the dissociation equations. Due to the presence of these ions, these charged particles, we have what we call electrolytic solutions. We've already discussed this. These are solutions that can conduct a current, okay? And the reason why is due to those charged particles floating around in the solution. So when you put your salt in water, right? When you take your NaCl and you put it in your water, you do not have sodium NaCl chloride particles floating around. You have sodium ions and you have chloride ions. Down here, when you take your sodium sulfide and you dissolve it in water, you do not have sodium sulfide in the water. You have 2 sodium ions for every 1 sulfide ion. It is utterly important that you balance these equations. Let me get a different color there. That these equations are balanced such that there are 2 sodiums here and we have 2 sodium ions over here. Okay, that's how ionic compounds dissociate. If we had, never mind. So covalent compounds do not do that. Covalent compounds are not composed of ions, therefore they do not dissociate to produce ions. So let's look at a quintessential, I don't use that word very often, covalent compound, and let's dissolve it in water, and we get the same compound just dissolved in water. Okay, notice no dissociation going on there, thus no electrolytic solution. Okay, this is not electrolyte. All right, so that's cool. Now let's look at the molarity of ions in solution. All right, and I've had a hard time keeping this short and sweet and simple, and I don't know why. So I'm going to simplify it here. Let's say that we've got sodium chloride, solid, sodium ion in the solution, plus a chloride ion in the solution. If this is 2.00 molar initially, then we end up with 2.00 molar sodium ions and 2.00 molar chloride ions. And we actually end up with 0 sodium chloride ions, right? And the reason that the molarities are the same is because it is a 1. Let me see if I can get a better color. 1, actually, let's put that here. There is a 1-to-1 ratio, and there is of sodium ions, and there is a 1-to-1 ratio of chloride ions. So we see the molarities are the same. Let's change the subscripts, and we'll look at what we looked at a minute ago. Sodium sulfide solid placed in water will dissociate. Now that is an S. It does not look like one. It will just, that does not either. It will dissociate to produce 2 sodium ions, and 1, all right, 1 sulfide ion, such that it's still balanced. These are the ions that will be floating around in the solution. There will be 2 sodiums for every 1 sulfide. Okay, I want to make it clear that if you do not put the charges on the product ions, it is wrong. Atoms and ions are very, in my opinion, different species, okay? So you've got to put the charges in your dissociation equations for your ionic compounds. Otherwise, it's utterly wrong. Shows that you don't know really what you're talking about. Okay, so there's your dissociation equations, and we were looking at our molarity of ions. Let's say that this is 2.00 molar sodium sulfide, all right? Well, there's there are, okay, 2 sodiums. Let me make that more clear. There are 2 sodiums, change the color, we've already used that color, 2 sodiums. There are 2 sodiums here for every 1 molecule. So that means my concentration here is multiplied by 2, and I'm actually 4.00 molar. Let me put that number on bottom. I'm 4.00 molar sodium ions. All right, 4.00 molar, because there, for every 1 of the compounds, there are 2 sodiums. So the concentration of sodium is doubled. For every 1 of the compound, there is only 1 sodium. So for every 2.00 molars of the compound, the sodium is also 2.00 molar. And we would be left with none of this, because we're at this point, we're assuming that it is all dissolved, okay? So the concentration of the sodium would be twice that, the concentration of the sulfide. Let's look at one more here. X2, Y3, solid, put it in water. We would have 2 X's, and we could infer that those X's had a 3+ charge, right? And we will have 3 Y's, and we would infer that they had a 2+ charge, right? Okay. You can always, if that confused you, ask me about it. I'll go over it in further detail. If this was 1.00 molar initially, then since we have for every 1 of the compounds, we have 2 X's, this would be 2.00 molar. And the Y over here, for every 1 of the compounds, we have 3 Y's, so this would be 3.00 molar, all right? And at the end, we would have none of our compound, because we have assumed, in this case, guys, complete dissociation. Everything went that way, okay? We will not see that change for a long time. All right, anything there you have a question about, you need to ask, okay? So let's look at that in terms of particulate diagrams. And in this case, we're just going to look at how these would be represented in solution. So I've got a 1 liter solution of, let's make that bigger. We need some more space here. We've got a 1 liter solution of a 1.00 molar LIF. And over here, we'll have a 1 liter solution of a 1.00 molar, let's say MgF2. I'm not going to, okay, so we'll do Li will be blue and F will be yellow. Those colors look good together. So all I'm going to focus on here is that for every Li, 1, 2, 3, 4, 5, there should also be 1 F. So we see that it is a 1-to-1 ratio, 5 particles of each. I'm going to actually change this to make this 5 molar because that only makes sense. And I'm going to do the same over here. Okay, I made a mistake. I should not have chosen 1. So I'm going to make them both 5. Now, for my MgF2, it is 5 molar, 5 moles per 1 liter. This is 1 liter. So there's 5 moles in it. There is 1 Mg in here, right? So I need to represent those 1 Mgs. I need to represent those 5 moles of magnesium ions as 1, 2, 3, 4, 5. Don't worry about where I put them. Maybe they should be spread out. I'm not going to worry about it. And our fluoride here, we have 2. Therefore, the concentration is doubled, right? Because we have 2 fluorides here for every 1 formula unit of the compound. So I should find myself with 10 particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles of fluoride. So just like with the gases, the number of dots could easily represent the number of moles. Because I have chosen 1 liter, in both cases, the molarity is essentially the moles, all right? And here I see that my moles need to be in a 1-to-2 ratio. 1-to-2 ratio. And over here I have a 1-to-1 ratio, right? If it was referencing this substance here, I would have a 2-to-3 ratio. Okay. And just to finish this up so that I try to cover everything that you're going to see on your work, concentrated versus dilute. Yeah, you know that, I'm sure. More solute, less solute, more solvent. And this is all relative, guys. Right? It's all relative. So we could talk about a concentrated substance maybe looking more like this. And I'm just going to kind of go about it. I'm not going to draw the water. I'm just going to color in the water, but those are literally water molecules. And then I've got I'm going to just draw my positive ions, my negative ions, positive, negative. All right. Oh, this is concentrated. So what I'm going to do is I'm going to draw a lot of positives and negatives because it means there's a lot of solute in here, right? There's a lot of stuff going on in here. I do need to make sure that whatever it is in the correct ratio, right? Is it 1-to-2 ratio, 2-to-1 ratio, 1-to-2 ratio? I think I did it right. If we are, so this would be concentrated, right? There's a lot of solute, lots of solute particles. And, you know, it always per volume of solution, right? Right? You could have a lot of particles, but the volume be huge, then you're not concentrated. But here we'll kind of have the same volume of solution, right? And here we would have just a few solute particles, right? So this is a diluted, right? Small amount. Of solute per volume of solution. Right, I'm going to do this abbreviation right here for solution. That's common. You guys know that stuff, right? You know that stuff. So, you know, what we did is we just talked about real quick how these ionic compounds dissociate into their ions, and that the subscripts over here determine the number of moles present over here. Because these are ions on the product side, we have an electrolytic solution. Because they dissociate into their respective ions and they're balanced, the concentration of the ions in the solution is determined by the number of those ions, number of moles of those ions present, which is in effect determined by the subscripts of the element in the compound. I'm feeling like I'm making sense. If not, I'll be happy to elaborate, okay? The other thing, we just kind of looked at that, and then we just talked about how particle diagrams, you need to ensure that you pay particularly close attention to what the volume is and how that relates to what the moles are, right? Because I have 1 liter and my molarity is 1, that means 1 liter is 5 moles. That means I have 5 moles. And I had already determined that it was a 1-to-1 ratio. So I had 5 of each. Here I had 1 liter. Every liter was 5 moles. So there are 5 moles of the compounds. And the compound, in fact, is a 1-to-2 ratio of cation to anion. So I should have twice as many anion particles drawn in the solution. Okay, remember, and I've gone over this several times, we're about to be done here. If you have to draw the respective cation and anions, and if you have to, then you will. If you have a question like this that comes up, you'll probably have to make the cations, oops, let's make this my cation, make the cation smaller than the anion, all right? And if you need to show the arrangement of water around, make sure that the partial negative N of the water molecule, the oxygen, is attached to the cation. Make it obvious just with the size of your circles. I didn't really do a good job there and there, right? Go like that. Maybe there'll be a key or they'll give you a key. And over here, make sure that your hydrogen, partial positive hydrogens, are attracted to the anion, okay? Because that only makes sense. If you have questions, please ask. It's okay to have questions. I only drew 2 because I had no directions. You may not have any directions either. I'm going to stop it at that. I am going to make a 3rd video of something that I think is worth your while in terms of understanding and comprehension. It'll be a fun problem to work through, okay? So that's that. I'm going to stop. I hope I covered everything. If not, I'll bring it up later. No problem. Okay. Bye. Good night.